Hey everyone, today I was hoping to give an overview of autoencoders from a mathematical standpoint, as all the resources I've seen online are mostly coming from either a full beginner standpoint or from a computer science background. So I thought it'd be good to have a background introduction to people who know the mathematics, so they don't have to sit through all that boring intro stuff. So, at its core, an autoencoder is a neural network with a deceptively simple objective: perfect reconstruction. We want to train a network where, given an input vector x, the output x hat is as close to x as possible. So, if you look at this objective, you might ask, why is this difficult? Can't the network just learn to simply pass through the data unchanged? Well, if we maintain the same dimensionality throughout the network, the answer would be yes. The network would simply learn the identity matrix. So to prevent this trivial solution, and force the network to learn something actually useful, we constrict the network architecture in the middle, reducing the dimensionality. And we call this point of low dimensionality the bottleneck. Because of this, we can now see the full architecture as split up into two distinct functions. The first is an encoder, which maps the high dimensional input x to a lower dimensional vector z. And we say that this vector z exists in the latent space, and we call it a latent vector. And then we have a decoder, which maps z back to the original dimension space to reconstruct x hat. Now, because the dimension of z is significantly lower than x, the network can't just memorize the input. It's forced to actually learn a compressed representation of the data, extracting only the most useful features required to reconstruct the input. One really cool thing you might have noticed is this is strictly unsupervised learning. We don't need any labels on the data. All we need is actual raw data because the data itself provides the supervision. For those of you familiar with linear algebra, if we were to use linear activation functions, this architecture effectively performs PCA, spanning the subspace defined by the first k principal components. However, by introducing non-linearities like ReLU or sigmoid activation functions, autoencoders can learn complex curved manifolds that PCA misses. So how does this work? Why can we represent a complete image with a tiny vector? This brings us to the manifold hypothesis. So let's consider the space of all possible 256 by 256 pixel images, and imagine that each pixel is represented as a value in a vector. This gives us a vector space of 65,536 dimensions. So as you can probably guess, this space is incredibly sparse. If we sample a point randomly in this space, you'll almost certainly get static noise, or another meaningless image. The subset of vectors that look like something meaningful, like digits, faces, or landscapes, is infinitesimally small. So we assume that the real-world data, or otherwise meaningful data, lies in a lower dimensional manifold embedded within this higher dimensional space. The goal of the autoencoder is to learn the coordinate systems of this manifold. The latent vector z then represents the coordinates of the image on the manifold, rather than in the ambient pixel space. So this gives us two main benefits. The first being compression. We can store the intrinsic coordinates z rather than the ambient coordinates x, with z being much, much smaller. And the second is manipulation. If we move along the axes of the latent space, this should allow us to interpolate between images meaningfully, whereas linear interpolation in pixel space just gives us ghosting, or just gaps of noise. Another benefit of manipulation is that if we sample a point in the latent space, we can expect to get a meaningful result with a much higher probability than if we just sampled from the ambient space. So you might be wondering, what is this even used for? There's tons of uses, but a classic application of this specific geometry is image denoising. So let's say we take a clean image and add some noise to it. We're essentially taking a point on the data manifold and perturbing it so it falls off of it. If we were to train an autoencoder on clean images, it learns the shape of the manifold. And when we then feed it a noisy image, you can imagine the encoder projects that point onto the latent space, the data manifold, and the decoder projects it back. Effectively, the network snaps that noisy point back to the nearest point on the manifold, removing the noise and preserving the key structure. However, these standard autoencoders have their limitations. One of them is spatial invariance. Fully connected autoencoders ignore local spatial correlations. For images and text and almost all data, this is really important to know. And so we almost always use convolutional autoencoders with images to respect spatial hierarchy. And the second is the continuity problem. Despite what we hope for, often the latent space is disjoint. There's little islands of key points, and in between them there's big seas of noise or useless garbage. So in general, the manifold is not continuous or smooth. To generate new realistic data, we really need to make sure that the latent space is continuous and smooth, so that when we sample a point, we can be pretty confident we'll get something meaningful from it. This leads us to variational autoencoders, which introduce probability distributions, and in short, enforces that the latent space follows a standard normal distribution. We're going to cover VAEs and other generative architectures like UNets later on. I hope you learned something from this, and thanks for watching. This is my first time making educational content like this, so I'd love to hear your feedback on anything that would make it easier to follow or any topics you'd like to learn in future.